I'm going to take a deeper dive into this modeling vertical motion Desmos graph by adding some solutions and really nice labels for those that convey a real precise amount using square roots, which will involve some coding using the math specific inputs that it requires here. Now, if you want to follow along, it would be good to check out the last video, which really had the same title and covered the 3 different models that were given, sort of like the benefits of each, and I also added some points into those to be able to center these when needed. Picking up where I left off, I'll take a look at this factored model and start with this factored version with 2 given zeros. I can use this quadratic function to find a solution at an inputted y value. The first step in this process of determining a solution is using the quadratic formula to, in this case, I'll define a third point. I'll call it t sub 3, which needs to occur at a designated y value. Now, what you would really need to do to fully work this out is sort of write out this function. What we want to do is set the function to a value. Let's call it y3 just to go along with that t3. So I'll have y3 equaling this whole right-hand side. But then we need to zero it out to be able to use the quadratic formula. So you can imagine subtracting y3 from each side to get this y0 minus y3 on the right side. And that is exactly what we'll need for our c value, like so. Now, I've come across this problem before. Right away, something tells me that this is wrong because I don't really imagine that it should be graphing a horizontal line. If anything, we're solving for a value of t, so you would think that would be a vertical line. Clearly, something has not worked here. And what actually happened is it mistook what I'm doing. I wanted it to prompt me for a slider for y3, but it didn't do that. So it kind of messed things up. There's a couple different ways we can work around it, but I recommend just adding an input. It can even be below, where you define this variable y3. Y3 is going to be some value that we want to solve for. So for example, I could initially set it to 9 meters. And now T3 is getting a value, and I actually should be able to plot this if I plot T3 and Y3. Now this label actually turned into a vertical slider all on its own just after I typed that in. And that's exactly what it should do because we've set Y to be a variable that can move, and we've defined T3 based on a bunch of defined variables. So every single variable letter that we see here has been defined as some number, so it is calculating out T3 to be a value now, and we've plotted those two together. So T3 is based on Y3, therefore it's almost like we've kind of changed the inputs and outputs. We've given ourselves an inputted Y value based on the slider and an outputted T value here. So that's what solving is really about. What we've got here is almost like an inverse function using this quadratic formula. However, we're only going to get a value on one side of it. If you've covered the concept of one-to-one functions, you notice that this quadratic parabola is not one-to-one, therefore we can't find an inverse of it, and really we need a second solution. So I will actually make a small change here. I'll call this T sub 3a and make a copy of that. I should change my 3a in my point definition too. Make a copy of that, paste it below, and change it to 3b. And change it to a plus. That will give me the other mirrored solution on the left side of the parabola. Because this being an even function, we have this pair of points equidistant from this center line. We'll actually call this an axis of symmetry right down the middle. So we're looking for the other of the pair on the left side. We'll call it T of 3b. We've got it here. And now to graph that one separately, I've got my T of 3b and Y of 3 left and right equidistant, and you'll be able to drag both of these really, and you could create a horizontal line connecting the two with Y equals Y3. And I'll just make all of these kind of the same green color. This is my set of solutions based on that y value. In some of my other videos, I've talked about limiting the domain, and we could easily do that here. We could limit this down to a graph where it starts at time 0 and goes up to our solution, which was right above there at t2. If you wanted to limit the domain, you could do that, and there we see that this point on the left stops really being relevant, and at a certain point so does the one on the right. And now what I'll do is add a label starting with the point on the right here that will really convey a little bit more information more specifically. So this label, this was for the 3A, which was on the right side. When I add it, it automatically tacks on this rounded version. And what I'd like to do is add more detail to that. In other videos, I've showed how to type out written labels like x-axis, y-axis, or solution. So you should check out my other videos for that. But this is a wholly different approach. In this demonstration, I'm going to actually convert this whole quadratic formula into something that we can convey that will hopefully not be as messy and as much to look at, and just have some simplified numbers. Maybe not as simplified as we could if we're doing it on paper, but at least a start, and then you can find your own path that works. Some people will sort of work things out on paper, type it in, then it's not really a dynamic graph. I'm kind of finding this middle ground in between. So what I'll do is I'll copy and paste this entire input on the right hand side of when I defined my t value, and I'm going to put that in as an x coordinate eventually, but let's start with just kind of building this up. Let's just see what it looks like when we paste this. Okay, we've got really a lot to it. I haven't in my videos really talked about some of the specifics of what we're seeing here. This first one is a fraction. It's saying we have a fraction, and then we have a bunch of things in braces for the numerator, and then some for the denominator. We've got a lot of extra stuff, and if you've ever looked in one of my companion documents, you've probably noticed there's a lot more here than you might think you need. And that is actually true. You don't always need to say left. If you had just typed a parenthesis, it would have been fine, but it helps with nesting parentheses, or it helps make it look nicer when you kind of have things nested inside each other. Also, for every single subscript and exponent, we're seeing braces. We don't necessarily need those, but it is there for clarity. And when we start having multiple things inside these, for example, when I have a subscript of 3a, I would need the braces or it would get confused along the way. So this is really getting into some coding properties that really translate to a lot of different areas. Now I'm going to just take what I have and make changes, not necessarily creating anything new, but swapping things out for numbers. Now the first thing we really need to do is convert it from a typed input that makes no sense into the nice looking math that like we see here on these inputs. And we need backticks on the very front end, left and right sides of that. So we have backticks around the entire thing, and now it looks like it did when we inputted it, which is great. So that we're partway there. Now we need to swap these variables out for numbers. I think that there's different ways I'll handle different pieces. In the very front, we have a negative b or negative v sub 0 in front. I want that to just be a number, a negative number. So the negative is already there. I want to turn this v underscore 0, and you don't need those braces if you want to make that a little simpler. It's just one number that we're putting in that subscript. So our variable is those three characters right there. V subscript 0 kind of looks like a little winky guy. We're going to put that inside braces with a $sign in front. And now the winky guy comes out to be a negative 10, which it's the $sign and the braces is basically saying, give me a number here, evaluate this quantity. It works for a variable. It does not work necessarily for entire expressions. So that's why inside the square root we need to handle it differently. We've got a whole expression in there. It will work a lot better if we define this as a variable. I'm going to call this D3. This is the discriminant for that third point that we use. The first two were the solutions on the x-axis, or the zeros I should say, And the third point here is going to be tied to that D3. So that is the discriminant that goes inside the radical. It unfortunately does not come out to a whole number because A has a decimal. A is that gravitational acceleration. That's some kind of long decimal that we've rounded. So this is the one point in the process that doesn't have full precision. However, putting that nested inside the square root is going to help us out and give us a little bit more precision that we can communicate to the viewer. Now I need to come down and find that square root. That's SQRT, which is something that I just type in Desmos to turn into that radical sign, and find the inside of that, which is our discriminant. So you have to follow the braces. We've got a bunch of braces showing subscripts and exponents along the way, but somewhere down at the very end, I have that right side of that brace. I think I can delete that and see what I've got. So there's a pair of braces for the square root. And now I'm going to actually zoom in a little bit more and see it better. And I've got a pair of braces for the fraction numerator and a pair for the denominator. Within that square root, I have D underscore 3. And we see that the label shows the D subscript 3. And put the dollar sign and the braces around that variable. And now we've got a value inside the square root. The very last one is converting 2a into a number. I'll need to define one more variable right under D3. I'll add another one. I wanted to use D for denominator. I could call it D4, but that seems different. So why don't I call this one, you know what, I'm just going to go with E3 because it's the next one in the alphabet. Looks like that's going to be fine. So E3 is just the 2a value. There we go. So that's the number that I want to put in the denominator. It actually ends up being the gravitational constant. Oh, so we don't even need that step. That's kind of nice to learn. Let's go in here and see what happens if we just put G in the dollar signs. There's that 9.81. So it ends up working out that the whole quadratic function is over 2a, and a was a 1/2 gt squared. So if we double that, oh, we need it to be negative. That's the other piece that I'm missing there. I need a negative g in the denominator, and that should work out. So 2a, I can just double check here, negative 9.81, and I've got negative 9.81. Now that is the x component, or in this case the t component of the ordered pair. If I want to create the whole ordered pair, I'm just going to continue building now with some parentheses around this. And I want that y value, which is actually this y value that this is all based on. So remember, if we go back a little bit earlier in the video, the idea was we want to have a solution, which is a given y that outputs an x, almost like an inverse function. And then we created the two versions of it because it's not one-to-one. So now we're plotting it, and we just plot that y value. So the y value is determined by the slider. We've got it defined right there. That's almost like the easiest part of all of this. Just don't forget the dollar sign and the braces. We can do that y underscore 3. Now this is where that left-right part of the coding was a bit important, because you'll notice these parentheses, they just don't look nice. They're not really big enough. If you type this backslash and then type the word left, and down on the right side, we need the right component of it. So backslash right. And now if those are paired up, it will match them and make them the same size and make them a bit larger if need be. So I think that there was some of that in the original coding within that square root where it had that left and right coding. But this is the end result. So it's that backslash left and then a left parenthesis and then whatever needs to go inside there, which is a fraction containing a lot of different stuff. Now this can really, getting to know these kinds of processes, it really enhances your order of operations skills as well. So it really does help to dive into these. And now you can decide if you want to add more to your label than that. You can label it as a solution. Like I said, I've covered that in other videos. And if you want to place it in a certain spot so it's not moving around on you, I think that can be helpful sometimes as well. So you can go ahead and try to do that left point labeling on your own. It's a really great practice, like I said, for coding.